Okay, so now I've shown you how to make confidence intervals and p-values by estimating standard error and then doing the standard thing that we already know how to do. So now you can have a confidence interval. Great. What do you do with that? How do you interpret it? Well, it depends on the question that you're asking. So let me show you why it's kind of a problem to try to interpret these things purely descriptively, or why, at least when you're doing that, you're kind of always just getting a vibe. So recall that the coefficients have a joint sampling distribution, right? For every data set that you get out of your population of possible data sets that you could have sampled from your population of people, so population of data sets, every one of those data sets, you have a different estimated regression coefficient, set of regression coefficients for them. So your beta A in this case and beta X hats, you have some kind of joint sampling distribution. And in this example, it looks roughly like this. This is an approximation, but this is roughly what it looks like. And in fact, we know by the theory that I presented in the previous section that this joint distribution is actually jointly normal. And so the marginals of both of these are normal. And in fact, any linear combination of these coefficients is normally distributed. So it always will have this kind of bowl-like shape, or really it's not a bowl. It's like a normal distribution in multiple variables. It's this like bell curve that if you can like spin it around. Think of that like that. So interesting thing happens, which is that when the predictors are correlated, the coefficients become negatively correlated. So this is different data generating processes. Under different data generating processes, how do my coefficients, what is the sampling distribution of my coefficients? So here, for example, I have two predictors, X and A. And here I have A depends on X in some way. And so that induces some kind of correlation between A and X. And because of that, actually, we have this joint distribution where for example, you're more likely to get high values of beta A when you're getting small values of beta X. And you're more likely to get small values of beta A when you get a high value of beta X. And this actually becomes quite extreme, and it depends on the correlation between, or covariance between x1 and x2. These are now two different predictors. And you can see that when the predictors are independent, there's actually really no relationship between beta 1 and beta 2. You're just as likely to get a high value, a big coefficient for beta 1 when there's a small coefficient for beta 2. But when they're highly correlated, getting a really big value for beta 2 basically implies almost deterministically that you're going to get a very small value for beta 1, relatively speaking. So here the true coefficients are 1 and 1. But here I'm getting 1.2 for beta 2 and 0.8 for beta 1. Really, they should both be 1. So why does this happen? And you can show this yourself if you want in simulations. Why does this happen? Why is it that they have this joint distribution that becomes skewed this way, where they kind of depend on one another? And it's the reason is that it's easy to split the difference between coefficients many different ways if those two coefficients are basically encoding, if those two covariates are basically encoding the same information. So forget about all that for a second, and let's just look at this very simple case. Let's say you have two variables, x1 and x2, and they're basically the same value, okay? So an example of this is like height and weight, right? People who are taller are pretty much always heavier. People who are heavier are generally also taller. So they're not exactly equal, but imagine it maybe even in an extreme scenario where you had somebody's height and you just doubled it, and you had another variable in your data frame that's, you have height 1, height 2, and they're the same value, okay? So they're basically the same thing. So now let's say you set up your regression model, and you evaluate the MSE of this model. So here it's 5 times x1 plus 1 times x2. That has some kind of MSE, okay? Those predictions have some error. And now let's consider the fact that I can move, since x1 and x2 are basically the same number, I can move x1, one of the x1s from over here to over here and call it x2 because they're equal. So I can redistribute the effect of x1 to x2, or vice versa. And so this has about the same mean squared error, but the coefficients are different, right? And I could do this even more extremely. I could have So here I'm plotting the coefficient values that I'm getting. So these coefficients are 5, 1, and this is 4, 2, and this is 1, 5, right? And all of these models have basically the same MSE. It's really hard to tell them apart. And so what's going to happen, or even this, right? We can have 7 and -1, okay? So what's going to happen is we get this kind of mean squared error just that is, it has a very long, narrow valley in it, okay? So if you're trying to find the minimum value, yes, the minimum value might be here, but it's going to be very data dependent, because if I have a different data set, that minimum could be shifted kind of almost anywhere in that valley. So here's another perspective. Let's say you have data that are distributed like this. So here's x1 and x2, and this is the scatter plot of x1 and x2. So as you can see, x1 and x2 are very highly correlated, okay? They depend very closely on each other, right? And let's say these are our y values that we have. And now let's do regression. Let's say this is the regression plane, one possible regression plane that we could have. That captures the data pretty well. But I could also just rotate that regression plane a bit, and the mean squared error will be very, very, very similar, right? So all of these regression planes fit the data equally well. However, they all have drastically different coefficients in terms of x1 and x2. It's just that rotating it in one way kind of increases the coefficient of x2 versus decreases the one for x1, or vice versa. So it's really hard to tell what the true coefficients are when the data are like this. And so what happens is that the sampling distribution of beta 1, beta 2 is actually induced by the shape of the kind of mean squared error, right? So if this is my mean squared error, population mean squared error, then in any given sample, I'm going to be estimating the sampling distribution something like this or something like that. And that creates uncertainty in the coefficient estimates. So that's all kind of abstract, but let's see in practice what this does. So here I have a data generating process where x1 and x2 are very tightly correlated. Here x2 is x1 plus a little bit of noise, okay? And then we're regressing y on x1 and x2, and all of our, everything is nice, everything is linear. So I'm going to use the robust covariance anyways, but you could have used the classical and it would have worked here because assumptions are satisfied. So let's say if I just regress y on x1, what do I get? So here I get this, the coefficient, well, I'm not showing you the coefficient values, but they're both going to be about 1 here. But my estimated standard error is very, very small. It's super confident, right? It's super confident that the coefficient on x1 is whatever it is. And let me show you, I think it should be about 1. Okay, so here let's draw some data from this data generating process. And okay, let's look at the coefficient. 2 actually, sorry. The coefficient here is 2. Why? That's very interesting, right? Because the true coefficient in here, right? There is a true coefficient in this case because it's linear, and it's y is equal to 1 times x1 plus 1 times x2. So wouldn't you expect this to be 1? No. Why? Because I've not included x2, and x2 is basically the same as x1. So when I'm only regressing on x1, it's basically counting the effect of x2 as being the effect of x1. It's accounting for the effect of x2 by ascribing that to x1. So that's why I get a 2 here. And moreover, the variability of this is very, very low, right? It says I am damn sure that this coefficient is 2. And it's not wrong because here what we're estimating is this conditional mean, y given x1, which is actually very close, should be approximately, right, 2 times x1. Even though, in reality, we have x1 and x2, this conditional mean is 1 times x1 plus 1 times x2, right? But like I said last lecture, these are two different things entirely, right? There's no reason why this should really be reflective of this. So by adding in a variable to your model, you're fundamentally changing the thing that you were estimating. It's not just like, oh, it's better or worse. You're just asking a different question altogether. And so let's see what happens if I add this variable here, x2. Now let's look at the coefficients. Okay, so here, in this case, I'm getting coefficients that are a bit closer to 1 and 1, but you see they're not actually that accurate, right? We're getting a 0.68 and 1.4. And if I look at the variance-covariance matrix, let's just look at the diagonal. So and we can just take the square root, so we're looking at standard errors. Let's do the same here. Okay, so this is when I have x1 and x2, and it's giving me these pretty big standard errors. So if I built a confidence interval, these are like 11. The values of the coefficients that I'm estimating are around 1. So these are going to show no significant difference from 0, right? It's basically saying I have no idea if these things are positive or negative. Why is that? Because it's seeing that it could have, you know, if I redo this, it's accurate basically. So let me rerun this with different data set. Get different data set, rerun this. Look, the coefficients have changed drastically, right? Because in this data set, it looked like maybe the best way to do it would be give 5 to x1 and minus 3 to x2. And what happens if you sum these things? You get 2, right? So, and if I do it again, now they're both huge, okay? Well, sorry, no, that's the, run it again. There we go, okay. So now 19 minus 18. So there's just huge variability in the sampling distribution with different data sets. My x1 and x2 are varying wildly, right? And so when I do this, when I look at these covariances, this is accurate, right? This is actually correct. This is telling me, accurately describing the fact that there's a lot of sampling variability in these coefficients. Even though if I do it with just the 1, right? If I look at this here, it's telling me, well, for this regression model, there's almost no variability at all. Okay, it can estimate that this coefficient is 2 with a lot of confidence. And so some people will look at this and be like, okay, well, you shouldn't adjust for things when they're collinear. But you absolutely should if your question is, what is the effect of x1 holding x2 constant? If you want to ask, what's the effect of x1 when x2 is allowed to vary, okay, run it without it. But it should, what your model specification is should depend on the question that you're asking, not on the, you know, the kind of answer that you want to get. Sometimes the question is hard to answer, and that's the case here, right? So if x1 and x2 are very tightly coupled in the observed data, then it's really hard to know what would happen if you varied x1 holding x2 constant, because that doesn't really happen in the data that you have. And so the fact that these are big numbers is accurate. That it's just saying this is hard to know. We can't tell based on these data. You got to go get other data where you know these things are somehow more uncoupled. So sometimes people will say, oh, there's variance inflation if you add collinear variables, but it's not actually inflating. It's like you're just changing the question. It's not like this is the right answer and then it blows up because this coefficient is not comparable to this coefficient. They're just different quantities. And so here, like I said, this big number reflects the fact that the coefficient estimates are very sensitive to the sample that you get in cases where there's this kind of collinearity. But what this means in practice is that when you're doing a kind of descriptive analysis, it makes it very difficult. If you just have a bunch of things that you measured and you kind of adjust and you run your model, you press go, you look at the coefficients, you look at the variability, it makes interpreting these things pretty meaningless, because you know if you added more variables or you took away variables, these things would all change, and you're not thinking very carefully about what are the variables that are correlated. What's you know, if you had a clear causal question, you would be able to understand concretely what are the possible confounders that I need to adjust for? What is not being adjusted for? How would this change if I added them? Or if you're just kind of looking at everything in a gestalt, you're not thinking clearly about how these things are going to change or be different if you're adding or subtracting variables. So yeah, descriptive inference, I would say, is hard. And it just comes to the fact that you don't have a clear question, so there's not a lot you can say. So here's an extreme case of this. Let's say you have two regressors that are perfectly identical. Here, if you run the linear regression model, you're often going to get an NA. I'm just giving you a heads up in case this happens to you. That's often the cause, is that you have two predictors that are perfectly the same. And here R is basically telling you that, okay, it's not this situation here. It's not this kind of I still have a minimum, right, in this situation, but if they're exactly equal, I don't have a minimum. The minimum is this entire line, and so there's not a unique regression solution. Any of them are equally good, exactly equally good. And so R is telling you, I don't know. I really don't know how to do this. I'm giving you a value here, but an NA here. And same thing if you have multiple collinearity. So here, x1, x2, x3, none of these are actual copies of each other. But x1, x2, and x3 actually collectively only encode the information that's in x1 and x2, because x3 is a linear difference of these two. So you actually have the same issue here. So this is called multiple collinearity or multicollinearity, where you have several variables that actually only encode the information of a subset of those variables. And you'll often get these kinds of NAs here. You can also get this if you have more predictors than you have data. So if you have only 4 samples, but you have 5 variables, then that will actually mathematically always induce this kind of multiple collinearity. You'll always be able to construct x5 out of my x1 through 4. The proof of that is some linear algebra you don't have to really worry about. But it basically means you can't fit these regression models. You can't fit regression models with more predictors than you have. You can't even fit them. It's not a question of getting inference. You just can't even fit them. There's multiple equally good solutions. There's not a unique minimizer in terms of the beta that gives you the smallest prediction error. So that's a fact. However, this is easily solved using a technique called regularization. We'll talk about this more when we get into the machine learning stuff later in the course. You just have to give up on, you have to include some other penalty, not just mean squared error. You have to restrict your model a little bit. So that's just a bit about how, sampling, what is the question, how the sampling variability in the coefficients is impacted by collinearity. So typically, you'll see this if you're doing testing. So you may want to know, okay, I have a coefficient that I've estimated. I want to know, is that significantly different from 0? If I were to repeat this experiment multiple times, is it very likely that there's actually the number that I got that was, let's say I got a slope of 5, right? Is it possible that really the number is 0? If I ran a different experiment, I could have gotten -5, I could have gotten +4, -4, right? And really the sampling mean is 0. So the way that you would, you might test that is by constructing a p-value, right? Or by looking at the confidence interval and seeing if it spans 0. Alternatively, you can do the kind of like summary table that we showed before, as again, always use the robust standard error. However, if you're doing that, you can do that. You can generate those numbers. Those numbers will be actual good reflections of the sampling variability, assuming you use the robust standard error. The question is, how do you then interpret them? Okay, so here's some things that it would be very stupid to do. So of course, you would never even think of doing them. And of course, you can find a million published papers where people do exactly these things. Okay, so these come from Cosma Shalizi's book. It's linked in the syllabus. I think this is like the only section where it's referenced as part of the readings. I do really recommend that you read it. There's a bit mathematical, but you can basically skip all the like formulas and stuff and just focus on the intuition. But this is taken from there. So things you should not do. You should not say, well, beta was significantly different from 0, so this predictor doesn't matter. Okay, so there's so many reasons why that may not be the case, right? So for one, you could just have too small of a sample size, right, to see the effect that it is having. So maybe it has a moderate size effect, but you just don't have enough data to detect it, right? Similarly, it could just be collinear with these other variables, and because of that collinearity, the effect is being kind of spread between the two variables very evenly. Makes it very hard to tell which is the one that's important and which is the one that is not. Or both of them, or what's going on. So the sampling variability is very high. Again, you just can't tell. You would need more data or different kinds of data to be able to estimate that effect. So another one, the converse of that is saying, okay, well, look, this coefficient has a tiny p-value, or the confidence interval is so narrow. So clearly, x really matters in for y. And the issue with that is that any p-value can be made arbitrarily small if you just have really large samples, right? So this is just what we were talking about p-values more generally. If you have a small p-value, that does not necessarily mean that anyone should care. It just means that you can that you're very confident in detecting whatever this effect is, no matter how small it is. So you could have a coefficient here that's equal to 0.000001. You have a tiny p-value. It's significant. Does it matter? Absolutely not. It does not matter. Okay. So let's just practice doing this concretely. Okay, so these are the coefficients I get. And now what we want to test is whether this smoker coefficient is statistically distinguishable from 0. So maybe the fastest way would be to do and this is based on the classical, so I should do okay, so I would like to look at this p-value here to test that this coefficient is substantially statistically indistinguishable from 0, and the p-value is tiny. It's not even showing how small it is. So basically, the conclusion is that we are very certain that this thing is not 0. The kind of best linear predictor value is far from 0. That's great. Now, does that mean that we care, or that we think smoker has an effect, a substantial effect on the charges? Well, in this case, the value of the coefficient itself is quite large, right? And so, this is on the scale of like $23,000. And that means that it actually is a substantially a useful predictor, right? That's a meaningful, practically meaningful amount of money. And so, yeah, it's significant statistically. It's also significant practically. And so that's interesting. There's definitely something going on here. Now, does that mean that this is causally attributable, right? The charges are causally attributable to smoking? Also, no. Because again, we could have omitted variable bias. We don't know if we added, maybe there's something else that we're not measuring here, that if we added this into the data set, it would change this value and it would make it much more uncertain, right? Something that would be collinear with smoking that's also affecting affecting the amount of charges. So I don't know what that is, but my point is that if you're just looking at this and not thinking about those things and not thinking, okay, how am I actually interpreting this? Is it purely descriptive? Is it predictive? Is it causal? You could come to some pretty wacky conclusions. So you can also test whether all coefficients are 0. This is, let me see if I have this. Yeah, so test whether all coefficients are 0. That is what this thing gives you down here. So if you just run summary of your regression model, and yeah, you just call summary on it, you'll get this long table out. You'll see this line at the bottom that says F statistic, blah, 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 p-value, this. This p-value is testing exactly that. Are all the coefficients statistically indistinguishable from zero simultaneously? So that's kind of comparing your regression model with all of these covariates in it to a regression model that has no covariates. It's just intercept, and saying basically, is the R squared different? It's different from one model to the other. That's the equivalent. The problem with this is that here, this depends on the normality assumption. That, again, just like these numbers do, these standard errors, these all depend on the standard linear model assumptions. So I recommend not doing this. You can also test for subsets. You can ask about, I'm not going to show you here, but you can ask, okay, are age and gender 0, but ASA is not. You can do this much more robustly using other software. So here's one way to do it. This car package and this linear hypothesis function, you can just put in your model object, and you can put in, this is what I want to test. Are both of these things 0? And here you can put white.adjust equals true to get the robust standard error version of this. And here you have the p-value testing this hypothesis. So that's pretty nice. So why do I show you this? There's also mistakes that people make when they're kind of asking about, okay, is this model any good, right? Or is this model just equivalent to having an intercept only, right? So more things that would be stupid to do. That is one thing you can do here. I was saying all my coefficients are significant, so my model is correct. Well, a lot of the hypothesis tests on the individual coefficients often presume the linear Gaussian model. Of course, if you do the robust standard error, that's not necessarily the case. But either way, what you're just testing is the best linear predictor of this 0 or non-zero. If I have my true conditional mean function could be very nonlinear, but the best linear function that approximates it could also have some non-zero slope. And so if you do the test and you're basically just asking, is that thing have a 0 slope or not? That's not the same as asking, is the true conditional mean nonlinear? So that really is not the same question at all. So you can't just look at your F test and say, oh, my model is good. Often people look at this and they say, this is like a kind of goodness of fit statistic. They talk a lot about goodness of fit, and if you have a good high goodness of fit, then somehow that model is reflective of the truth. And that's just not the case. Similarly, we'll talk more about this next time. People often just look at, they do some tests, either coefficient by coefficient or maybe in groups of them, and they just get rid of all the variables whose coefficients didn't have any stars by them, and then they rerun the regression and say, I got rid of all the stupid variables that didn't matter, now I only have what matters, I rerun it, these are the true values. Makes absolutely no sense. The reason it makes absolutely no sense is because of this. We already saw this situation here, right? In this setting, let's say I ran this model, I say x1 and x2, wow, both of them are highly non-significant, right? Because the standard errors are so big, they both cover 0. x1 and x2, neither of them matter, right? So then I'm just going to drop them both and say, hey, this model is only as good as if I'm doing this by individually, I'm going to drop them both, and then I'm just going to end up with a model with just the intercept term, and say that's the better model, even though clearly, in reality, both of these variables matter. It's just that it's just that it's hard to tell which one matters and by how much, right? If you were to do it, also you're going to get a different answer if you do it jointly, right? If you would say I think here if you jointly test, are they both 0? I don't know. Let's see what happens. So here's my data, and now we're going to do this kind of joint testing. Oh, I haven't fit my model. There we go. Okay, so this is what I was trying to show. So if you do this kind of joint testing for significance, Here I'm asking, are x1 and x2 both 0 simultaneously? And if I'm looking at just the individual p-values in this model, it's going to say, I can't tell. Individually, if I just look at x1, I can't tell if it's 0 or not. I can't tell individually if I just look at x2, it's 0 or not. And the reason is because I could have just put some of the effect of x1 into x2 or vice versa, and the model is about as good. So I don't really know which one is doing what. But if I jointly test, are they both simultaneously 0? Then that's going to give me a very low, very small p-value, because it's not very likely that they're both 0. In fact, the models that are equally likely are basically all the models where the total of the effect sums to 2. And so if we're basically asking, like, are both coefficients 0? No, definitely both coefficients are not 0. I just don't know which one is or isn't. So you can kind of use these things together to get an idea of what's going on. But either way, even if you're doing this versus the testing individually, you don't want to just drop coefficients because they're significant or not significant, or even if they're significant in some groups. One, because you're asking a fundamentally different question if you're running a regression model with different variables in it. Okay, done. And two, because of the other reason that we already talked about as well, the significance doesn't necessarily mean that it's not important for prediction. If what your goal is prediction, then if you drop something that's insignificant, it could be a very good predictor. It's just hard to tell, right? If it's this variable or that variable. So you could really hurt your predictive power by doing this if that's what you care about. Of course, in the causal setting, if you're doing this, that's awful as well, because if something is a confounder, it should be a confounder because you know it is, not because it has some relationship with the outcome. You're not testing here the relationship with the exposure. And so if it's affecting the exposure a lot, but just the outcome a little bit, and you get rid of it, boom, you've introduced bias. So we'll talk more about this next week, but really bad stuff that you should not be doing. Okay, so let's think about it a little bit more. Let's say I have a data set of Alzheimer's patients. The outcome is it's the result of a memory test given at age 70. And as predictors, I have the results of memory tests given at age 68 and 69. So my question is, can I somehow explain the memory test at age 70 using these previous memory tests that we've done? So I regress the final memory test results onto the previous 2 years' results, and neither coefficient is statistically significant. So is that surprising? Can I conclude that neither memory test is a useful predictor of the subsequent test, or that there's no causal relation between the previous memory tests and the subsequent one? And hopefully, based on the discussion we've just been having, you can tell me that the answer to that question is no, absolutely not. These things might be very useful, even if they're not statistically significant. And moreover, I definitely can't say a lot about causality because I don't know, what the confounding structure is here. I haven't really thought about that at all. I'm not even adjusting for any confounders. So a lot of difficulty there. The second question is, can you explain why this happened? And here you should be thinking, okay, well, if I'm getting not two things that I feel like should be significant individually, but together they're not, maybe there's some kind of collinearity thing going on. And that's exactly right. If you're asking about what somebody's memory tests when they're 68 and their memory tests when they're 69, they're probably very similar, right? People's results, maybe they're deteriorating a little bit, but generally there's going to be a high correlation. If somebody scored high at 68, they're going to score high at 69. If somebody scored low at 68, they're probably going to score lower again at 69. And that actually similar that should hold over at year 70 too, right? Which is what makes you think that the test in year 60 when they're 69 is going to be very predictive of their score at 70 years of age. But that also means that these two predictors that you're using are collinear, and therefore it's hard to ascribe the effect at age 70 to what's going on at 68 versus 69, right? Both of them are equally good predictors. They have the same information in them, roughly speaking, and so you could use either one of them, and that makes it hard to tell, right? Which one of them is doing the explaining. So that's why neither coefficient is significant. Now, what might be a better way to assess whether the previous tests are useful for predicting the latter result? So here we've defined the question more clearly. Let's just say all I care about is predicting the value of the test at age 70. I don't want to do the test again. Maybe it's an expensive test to run. I already did it at age 69, I already did it at 68. Can I just use those two values to predict what it's going to be at age 70? But if that's our question, then our assessment here should not have anything to do with the significance of the coefficients. We should be looking just at the measure of, some measure of predictive power. So for example, mean squared error. I can look at the mean squared error if I only use like an intercept-only model to predict the test at age 70. And I can look at the error if I add these two test results as predictors. And I can look at the error if I just add one or the other. And generally, you're going to see that the error is going to be lower with both of these, and probably substantially lower than if you had just used the intercept, which makes sense. It's obvious, right? That these things should be highly predictive. But you're not going to see that if you're looking at the stars, little p-values, because you're asking the wrong question and you're asking it in the wrong context, so you're not thinking clearly about what's going on.